Once such technologies start modifying the individual, then are you still talking to the individual who was there before they were modified by these technologies? And what if the actions they take are against what they would have done had they not had this technology implemented?
Thank you, Krishnan. Really appreciate you being part of Change. I Am Possible, which is India's first future tech podcast. So, for my guests who don't really know about you, I'm going to give them a little brief on who Krishnan is. Krishnan Thyagarajan is a research scientist in the hardware systems laboratory at Parc. His field of expertise lies in the physics and material science of nanophotonic system. He's engaged in applied electromagnetics research for application including in the biomedical, clean energy, and optical device sectors. His other areas of interest include biomimetic systems, which I'm really excited about, energy harvesting, scavenging, and MySpace, which is augmented reality. And he's currently the principal investigator for Parc's non-invasive brain-computer interface. They are amongst the 6 companies that is being funded by DARPA's program called the Next Generation Non-Surgical Neurotechnology, short for NTHE, for which DARPA has given a 4-year deadline period. So, Krishnan, thank you. Really appreciate you being part of Change and Possible. So, for the people who don't really know about what brain-computer interface is, so can you please start there? Tell us what a brain-computer interface is and what is an invasive to a non-invasive BCI?
What I would start at is at a level where you have a broader class of systems called human-machine interfaces. So that does not necessarily have to be brain. It could be any other part of the body. And the machine need not be a computer. It could be something mechanical. It could be something electrical, but not necessarily something which computes. So the broad system of things called human-machine interfaces has a number of smaller segments. And one of them happens to be brain-computer interfaces. And you can imagine the reason why brain-computer interfaces have taken such a forefront in terms of research is because the brain is the computing part that we have in our head and in our system, and the analogous part is the computer that you have in the physical non-biological world. So brain-computer interfaces essentially would consist of a means of figuring out what the brain is sort of speaking, if you will, translating that and sensing that by a set of electronics and sensors on board, shifting that knowledge to a computer, which then uses advanced techniques such as machine learning and artificial intelligence in order to really understand with the models that have been built as to what the brain is trying to convey, and then correspondingly translate that into an actionable outcome. So you can think of the situation that someone is thinking that they want to, say, move a certain limb. And the sensors pick that intent up from the brain, translate that into the idea that the person wants to move an object, and then that is acted upon a robot, for example, or their own hand, in case it's sort of a completely human interface. And in these systems, you have what are called invasive and non-invasive, and there's a third category in between, which people tend to call either minimally invasive or partially invasive. And the idea behind the three is that, of course, in principle, the most ideal situation would be where you have no surgery, nothing done into your head. You can literally wear something and directly be connected to your system of interest. But the way things started out initially, and sort of the first time, I think in 1924, Ansberger was able to record EEG signals, that sort of kick-started the idea of, okay, there is something the brain is speaking, and if we pay close attention enough, you can make sense of it and maybe take action on what sort of conversations are going on in the head. So invasive technologies started to pick up early on in the beginning because of the fact that there were a lot of concerns that needed to be addressed in the medical domain. So you needed to, for example, figure out how to help and rehabilitate people who have suffered from stroke, people who have suffered from a major spinal cord injury, people who suffer from Parkinson's, and so on and so forth. And these involve the need to actually have a surgery done in a process known as craniotomy, where you essentially open up the skull and then access the inner parts of the brain. Now, the completely invasive or the invasive devices that most people talk about include things like electrode arrays. It could include, in sort of preclinical trials, even things like graphene electrodes that people use. But those essentially start plugging themselves into the brain. So they go through the skull and then they go into the brain tissue. You have the next level of minimally invasive or partially invasive, where you still have to unfortunately do craniotomy, that is open up the skull, but then the sensors or the stimulators that you have lie on the surface of the brain. So they don't really poke into the tissue, but it suffices that they are close to the brain and inside the skull. And then the sort of most lucrative, if you will, or the most acceptable to a larger audience is a non-invasive system, where it would be something where you essentially wear it as, for example, a helmet, and you can use a bunch of electronics to dial in the sensors and the stimulators in your helmet to read out and write into your brain. So, of course, each of these has their own pros and cons, as you can imagine. And so what people use would depend on the interest.
Right. So brain, I think, 80 billion neurons and 100 trillion synapses, 80 billion odd neurons, and that's what makes us, right? How they fire and wire. All of five senses is an output of how our cognitive structure functions, right? And somehow that is still the least known part of a human body. At this point in time, some of the biggest names in the world have actually all jumped in and trying to understand brain. And I would like to give out a shout out to Brian Johnson. I think he's a hero in this field, because he is the one who's kind of like pushed it up there and said, we need to understand this part. If we understand a brain, how it fires and wires, because somehow if we know that, it's almost like a language, or like how we speak. Even the brain, how it fires and wires, has a language. And if we understand that, and if we are able to map it on a computer, I mean, that would be like super awesome for us as a human species, right? So how much do we currently know about a brain, and what research or technology, whether it's artificial intelligence, machine learning, what are the interfaces which could accelerate the understanding of a human brain?
Of course, the brain is an extremely complex system, so it's hard to really, as you correctly point out, figure out everything about the brain. And we have understood a very small fraction of what there is to be understood. But having said that, you can think of the analogy that often you can exploit a system or use a system without necessarily knowing all the details. So I think the interesting thing about brain-machine interfaces in general, brain-computer interfaces, is that it brings together a lot of interdisciplinary work. It could be neuroscientists, it could be physicists, electrical engineers, material scientists, because you have to make what appears to be a rigid system to work in synchrony with an extremely soft, supple, moist, warm system, which is the biological tissue, and make sense of that at a complexity which is non-trivial. So when these different branches of science come together to solve any given neuroscience problem, I think each of them brings their own skill sets, expertise, and points of interest in terms of what they want to understand at the end of the day. If you look at neuroscientists who come into the brain-machine interface or brain-computer interface domain, a lot of their interest lies in, as you said, figuring out what the brain is, how it works, what are the hidden parts. Can you sort of break down the response of the brain in order to figure out, hey, okay, if a person is happy, this is what is going to be the outcome. And so if I sense that this is what is lighting up in his brain, that means he's definitely happy, whether or not he shows it on his face. You have also psychologists and psychiatrists who come because, unfortunately, as much as technology has become ubiquitous in society, we have also it has taken a toll on our ability to actually maybe be as organic as we used to several decades or maybe 100 years ago. And so there's an increasing problem of mental disorders that is afflicting society for a number of issues. And in order to treat those effectively, you need to have quantitative information available. You need to have quantitative tools to be able to actually act on your information. And so psychiatrists look at brain-computer interfaces as a means of actually helping assuage people's mental issues and figuring out a bit more about the brain. Because as much as psychological issues, for example, are kept aside from physical illnesses, they are pretty much as realist. I mean, as real to the people undergoing the problem as a physical illness. So people are developing quantitative tools for that. Me as a physicist, I think I'm interested in developing the tools and understanding how sort of the brain works. But I don't necessarily need to know the exact details of the wirings of the system in order to make the maximum use of it. And it suffices to know a certain amount of level of detail in order to take action on any intelligence that you figure out. Having said that, I think as the technology has progressed over the last several decades, you've had a number of thrusts, including in the domains of material science, nanotechnology, electrical engineering, signal processing, which have all significantly enabled push what I would call textbook science to actually lab or market-driven research. And so that has given a lot of tools that have allowed us to understand more of the brain. And it's sort of it's like a chicken and egg, if you will, where you use the brain as an end to actually develop a tool to access it. But then the tools that you develop are used to actually understand the brain even more. So there's sort of a momentum being picked up right now where technologies that are developed are quickly translated into work that can be done on the brain to understand the brain better, which then helps develop better technology, which then helps develop a better understanding of the brain. So I think it's an exciting time to be working in this domain, but there is still a while to go before we can confidently say that we've understood a significant amount of the brain.
I wish you guys, everyone, the very best for it, because yes, like I said, I mean, we've understood so little of a brain, and in the future, when we are able to map what a brain does, and there is so much which might open up, I mean, so much that we don't know. Like, for example, you said, now we have the technology or tool to peep into the brain, kind of understand, if you're happy, now those are the neurons which are firing. If you're sad, those are the neurons which are firing. If you're depressed, now those are the specific, bunch of neurons which are going bonkers. Now, if we understand that, what is the best way to stimulate those parts, or maybe make sure that we could possibly treat those patients who are depressed, or make people happy? So what's the best possible approach?
That's also a very nice way to look at it. So let's take, for example, psychological illnesses or psychiatric problems right now. Currently, the ways that people use to assuage the problems of the patients is using chemical drugs, and which are effective because people to a certain extent have started to understand the pathways that operate in the brain and that affect unnecessary recursive thoughts, for example, or repeated firing of a certain region of the brain which makes a person go in loops. You can think of brain-computer interfaces potentially as a new form of an electronic drug, which essentially you can dial into and tune things like dosage, you can tune things like frequency, and with the advanced automated systems that have come in sort of manifested right now, you can even have things like closed loop systems which have used sensors on your brain to detect your mental state, for example. They use some sort of a machine learning AI algorithm to figure out that, okay, this person is in a mood which might trigger a certain unwanted action or might trigger an epileptic reaction, for example. And so it automatically then sends a signal to the stimulators as a part of the system which the patient is wearing in order to trigger or suppress the firing of certain parts of the brain. So you can think of it as a closed loop system which is constantly monitoring your state and affecting you. But having said that, I think there are a number of technologies that have really pushed the limits of what is achievable right now. Of course, in order to have any technology validated and applicable to humans, it rigorous approvals, it has to go along with clinical trials. But if you look at just the preclinical work that is being done, even in things, even sort of in scenarios where you're looking at animal studies, you have a lot of work done in the domain of optogenetics. I don't know if you've heard of that, but it's the idea that yes, and so there has been a lot of very interesting scientific work done on that in the likes of, for example, stimulating a certain memory of an event that never occurred. So I think if you look back maybe 50 years ago, people would have thought that such sort of technologies are just out of the realm of science fiction. It's not going to happen in reality. But people have started looking at such manifestations in animals. And of course, preclinical, these are far from humans. But that sort of shows you the power of such technologies and how they can potentially redefine what we feel to be our reality. And that's sort of one extreme of technology, which will take a while for it to be applicable to humans. But you can think of other technologies like electrode arrays, ultrasound, transcranial magnetic stimulation, which are all techniques which essentially are a mix of invasive and non-invasive. And they're mature enough that they're used for a number of treatments already to suppress or trigger parts of the brain on demand. So I think technology is definitely reaching close to what people would like to explore in theory. There's still a gap which needs to be filled, but I think the gap is narrowing down.
Right. So can you please explain to my audience what optogenetics is? And you also mentioned about graphene electrodes. So maybe you can just talk about these two.
Sure. So optogenetics is an extremely interesting idea that was developed a while ago at Stanford. And the idea was that you can genetically modify a number of cells in order to express proteins which are triggered by light. So you can imagine the case that you have, for example, a mouse in whose brain you have undertaken this process of genetic modification, which is not a very complex process now that it's become so mature. You then use light in order to trigger the firing of those cells or the suppression of those cells, which essentially translates to the fact that I can either turn on the switch or turn off the switch on my own volition. And this is extremely interesting because the advances in brain science have become so much that people know very well what sort of regions of the brain to trigger, for example, to make a mouse turn clockwise, to make a mouse turn anti-clockwise, to induce things like, to suppress things like anxiety, that you can literally tailor make the genetic modification in order to induce certain forms of behavioral change in the animal. I think for that to be applicable to humans, there is still some amount of validation that would need to be done. But if you look at the other question that you raised of graphene, it's an extremely interesting material which has been a favorite of a number of people in material science, physics, chemistry. And now more and more, because of its electrical and thermal properties and the fact that it's such a thin layer, people are using that to be almost two-dimensional electrodes in order to trigger parts of the brain or to record from parts of the brain. So because the brain is any organic tissue has an extremely low sort of stiffness compared to, say, silicon or wood or any other man-made material. The closer the material properties of the sensor or stimulator are to the brain when inserted inside the brain, the more acceptable it is to the body and the less adverse reactions it will produce. So graphene has this huge advantage of being extremely thin, malleable, can be made into sheets, and can both stimulate and record, giving it a huge advantage over the more conventional but much more tested and much more accepted electrode arrays, for example.
Right. So I mean, I have read about how the C. elegans worms, it has somewhere around 320 or 300 odd neurons, how they have been completely researched upon, we understand how it fires and wires, and it was also uploaded on a connectome, and the connectome behaved exactly like the real or the physical C. elegans worm. So I know about that, but the advances in BCI is, like you said, I mean, it is growing phenomenally, and this was, I believe, I think around 6 or 7 years back, when somebody had attempted something like that. So yes, you said, we are experimenting with like your rats, dogs, monkeys. So what are the insights that you have got from invasive BCI? Who are the leaders who are fronting something like that, and where do you see that technology going?
As you pointed out correctly, to translate anything from animal studies to eventually human studies is a non-trivial long process. But the reason why animal studies are done are to get insights and learnings into what can be applied to humans. So with the number of scientific sort of research experiments that have been done so far, there has been a significant improvement in the material compatibility to begin with. So earlier, people would literally put silicon shanks in. They would put electrode arrays, which would be extremely stiff and would not last long inside the tissue. These animal studies have definitely given a boost to the type of materials that are being considered for human trials. The other thing is that with the ability to actually access sensor signals and stimulate parts of the brain for a reasonably complex animal such as a mouse, you need to also be able to do real-time computation, signal processing in order to figure out, okay, what is the brain saying? What is the next step that I need to do? And that platform has given a lot of impetus to improve such techniques of machine learning, where you're not starting with a complex system like a human brain, but you're still starting with a very complex system like a mouse brain, and improving things like reducing the latency between figuring out what the brain is doing and then taking the next action, or stimulating the brain and then measuring that, okay, that stimulus has actually done what it needs to do. So on a much smaller scale with a reasonably large complexity, people are progressing towards an integrated system that gives them a lot of access to what they would like in humans in the long run. As far as experts are concerned, I'd say that there are a number of labs, and more so right now, a number of companies which are trying to push the envelope of bringing technology from the lab to the market. And I think you can look at long-term audience of such brain-machine interfaces to be of sort of two, three broad kinds. So one of them could be people who actually need it for medical cases and medical situations. For them, I think depending on the complexity of the situation, a few of them might be willing to go for much more non-invasive stuff if it gives them a much better quality of life. The other sort of extreme is brain-machine interfaces for entertainment, for example. And you can think of having a VR system which incorporates some sort of a brain-machine interface and gives the person a much more realistic experience in terms of a multi-sensory experience, which is not possible if you just display something in a screen. For them, I don't know, there might be still a fraction of people who would be willing to undergo an invasive surgery, but the type of the market that you would sort of cater to, or the type of audience that would accept the technology, would really weigh risk versus reward. And I think the more invasive technologies I foresee being more applicable to the medical cases than for the entertainment or augmentation cases, if you will. But having said that, there are still a number of cases in any technology that you pick up where there are these leading adopters who would be willing to undertake any sort of surgery in order to be the first to experiment with such devices.
Right. Yeah. So I've been invested in the virtual reality space since early 2016, and the reason I got into it was because I was excited or I wanted to one day be able to at least be either a part of it or build a full dive VR experience. And I guess, I mean, what's going to enable that would be brain computer interface. And I'm very sure that's maybe around 4 to 5 decades away, or maybe less. But give and take, I mean, I'm not a you cannot predict, but I believe it's somewhere around that's the timelines. And I think brain computer interface will play a big role in pushing virtual reality forward. As far as the invasive part, I'm sure by that time we'll figure out something which will be non-invasive and which will be much better. Talking about non-invasive, you are behind the principal investigator behind building the non-invasive BCI at Parc. So can you talk about what you're building and what's your vision behind it?
Sure. So what we're building is, this is with our collaborators at Stanford, we are building a non-invasive brain stimulation device. So if you want to call it, you can think of it as a write-in device, which is able to write into your brain non-invasively. That is to either excite or suppress parts of the brain on demand. And the technology that we are pushing forth involves a mix of using ultrasound and electromagnetics. So ultrasound technologies for brain interfacing, if you will, has started or has become much more mature in the domain of ablation. So you can think of ultrasound to ablate brain tumors, to ablate certain parts of the tissue of the brain that is actually dysfunctioning, for example. There is a shifting trend to use those capabilities learned with that process in stimulating without the intent of causing any sort of destruction. And the reason why ultrasound is extremely interesting is that it can go deep into the brain. It is an extremely mature technology that allows you to selectively stimulate extremely small focal volumes and use multiple arrays of transducers in order to actually steer the beam, in order to make any sort of complex spatiotemporal pattern that you would like. And sorry, the magnetic part of it is very interesting because if you think of it in like the physicist perspective, a neuron is like a charge, like current carrying wire. So electromagnetics immediately pops up because you can think of influencing the way current is carried in a wire using electromagnetics. So it's a combination of ultrasound and electromagnetics that we're using in order to affect the firing or inhibition of neurons through mechanistic or pressure-sensitive ion channels.
Right. So when you're building this, what are the applications that you foresee are coming out of your non-invasive BCI?
That's a very good question. So, for example, Parc as an institution, which is located in Palo Alto, started out in 1970 and has been a pioneer in actually user interfaces. And a lot of human-centric technology that we're using, in fact, even things like the Ethernet was invented at Parc, the mouse, the laser printer. So Parc has had this history of actually developing technology that brings people closer together, if you will. And what we see, for example, is, as you correctly pointed out, a larger and larger role of such brain interfaces in helping interface with either humans or other machines. It could be things like recreating scenarios much more realistically, like in the VR case. You can also think of training people to understand certain types of signals to imply something. So, for example, you can give them an extra capability to to understand a language of stimulation of the brain, which is not intuitive, but which they can learn by figuring out, okay, that when this, I sense this in my brain, if you will, that means I should be doing this, for example. So it's a subliminal way of communicating, and again, it comes down to the idea of user interfaces that brings technology easier to access for humans, and brings people closer together by interaction.
Right. You said extra capability, right? So what are the moral or ethical implications you see arising from something like this? When we have like a brain-computer interface, a working brain-computer interface, at this point in time, what it does is that obviously the ones who are you have a medical history. I mean, it's for them, and they go for the really invasive ones because it really helps them. But this technology is growing, and when it kind of matures, what do you see the moral and ethical implications rising out of something, a technology like this?
That is also an extremely good question, and I think it's a question that the entire community is cognizant of. In all the conferences that I've attended so far, there's almost always one session on neuroethics, looking at the implications of such technologies in society at large. And the nice thing about that is it brings together, again, philosophers, lawyers, social scientists, ethnographers. And I think you can have the understanding of, okay, what is augmenting a human capability? You might even consider things like spectacles to be an augmentation of human capability, because as people grow older, naturally their eyesight would decline. But now I have a device that I'm wearing that gives me extra powers over someone else my age whose eyesight might be weaker. So there are, I think, various levels of ethical concerns. One of them is sort of legal in terms of, okay, what is augmentation, what is permitted. But I believe that in terms of ethical concerns, there are a lot of open-ended questions that need tying up, and it involves the presence of governments, of industry, of scientists, of civil society, in order to figure out sort of the limits of utilization of such devices. What would be the fine line dividing the creator and the creation, if you will? So you can think of brain-machine interfaces as being created by us, but if you foresee that it has the capability of influencing my own thoughts, then it's actually changing me rather than me changing it. So then the roles reverse, and it becomes the sort of the creator, and I become its creation. And I think where that fine line is something that needs to be carefully considered. Especially because I think, unlike other sort of physical medical technology, any technology that interfaces with someone's personality or ability to interact with others from the definition of who they are needs to be very carefully considered, because once such technologies start modifying the individual, then are you still talking to the individual who was there before they were modified by these technologies? And what if the actions they take are against what they would have done had they not had this technology implemented? So there's a lot of ethical questions that come up. Some of them are similar to what you would consider even for self-driving cars. For example, who is responsible if a self-driving car has to choose between hitting a child versus hitting an elderly patient? In a similar sense, if you have a brain-machine interface, the subsequent actions taken by the person, who is responsible? Is it the person? Is it the company that built the device? Is it the ethical board that manages certification of such devices? I think there are a lot of open-ended questions which will get sorted out in due course.
Right. These are like really, really deep questions, because, and I think we need to come together as a collective and address those questions, because we are at the cusp of the fourth industrial revolution. If you see, almost all of those disruptive technologies have the potential to transform mankind. And you rightfully pointed out, technology is a double-edged sword, right? I mean, in the hands of a good human, it can create magic for the entire society. And in the hands of somebody who's not with the right intention, can also create a dystopian future, right? So there are, like I pointed out earlier, there are people like Brian Johnson who's really push driving this conversation. And obviously there is Elon Musk who's raising awareness about this technology and this need to kind of invest in it, research in it, build and come together, because this technology can transform mankind. So tell me, artificial intelligence. How important a role is artificial intelligence playing in brain-computer interface or understanding brain? And do you think that if we kind of understand our brain, will it play a role in enabling the conversation forward to being an artificial general intelligence?
Okay, so artificial intelligence is sort of a tool that has been developed out of inspiration provided from how the brain works. Having said that, I don't think, it's sort of a domain which literally is trying to mimic the complexity of connections that you would have in the human brain to reproduce the human brain in silico, if you will. Having said that, I think AI as such is an extremely useful potential tool in order to get a grasp of handling the complexity of data that comes out from the brain. So the brain is an amazingly powerful instrument because despite doing so much that it does, it consumes only 20 watts of power. And it is surprisingly efficient, considering that even for a simple thing like figuring out a cat amongst 1,000 different images with machine learning, you need to spend a significant amount of computational power to do that and train the system before it actually figures that out. So AI and machine learning, although they're sort of two separate topics, I think both will play a crucial role in being able to get a better grasp of the brain, but also helping develop more efficient tools that can interface with the brain. As far as going into artificial general intelligence is concerned, I think there is the AI domain is sort of not intentionally trying to converge to mimicking the brain completely, and the brain, sort of the neuroscience community, is also not looking at AI as an inspiration to see what the brain might look like if it were to be just broken down into wires and nodes and what you will. But together they can mutually help each other out, because a lot of AI and machine learning progress depends on the understanding of how the brain works. How does it sort of figure out the concept of appleness or blueness, for example, which was non-trivial to do the first time it was done. At the same time, I think the brain, in order to, if you consider it as something which is communicating with the outside world, in order to efficiently extract the maximum amount of information that it wants to convey in a form that we can understand, AI and ML will be really useful in doing that, simply because also the amount of data that comes out of the brain is humongous. And if you want to take any real-time actionable work on that, it needs to have the backup of an extremely powerful AI ML tool.
Right. You said we are not working on, the AI researchers are not working on mimicking the brain, but somehow it feels like virtual reality. All that we're trying to do is mimic the physical reality, right? I mean, we working on mimicking how we hear sound, right from your stereo sound. We trying to get into ambisonic spatial sound, how we can like move your left, and when we move to our left, we get the sound from that side more clearly. With a visual, we trying to mimic how exactly our eyes see, to how we sight, sound, smell, touch, taste, whatever. What virtual reality is doing is nothing but trying to mimic our physical reality. So somehow I feel if we do that same with our brain, if we kind of understand that, we will open up some really huge Pandora's box. So what are some of the applications that current applications at this point of time for or invasive to or non-invasive BCI that excites you the most?
Okay. So just briefly touching upon the concept of reality, the fact that the speed of sound is so different from the speed of light, you can literally take that to pose the question that how is it that the brain is creating a worldview that is consistent when, in principle, the sight of something should have reached me before the sound does, but I still see it occur almost simultaneously. So the brain itself is doing a lot of computation in what we believe or perceive to be reality in order to give us a consistent worldview. And I don't think that you can pull yourself out of that scenario and see what the sort of absolute objective reality would be like, because it's hard to, it goes into the sort of philosophical debate of what is reality and does the moon exist when you're not looking at it, sort of the typical questions. But I think as a means of recreating as close to a realistic experience as possible, I think that could be a nice objective of such devices, because very often you have memories from the past, good memories or nostalgic associations, or I don't know, you want to recreate the smell of something that your mother cooked when you were a child. And having technology that can help you recreate that at the click of a button in a much more realistic manner is something which is really amazing. And I think sort of many of the applications that would be mass consumable would cater to that aspect of entertainment and creating a sense of recreating something from the past or augmenting something as a sensory experience. So if you were to categorize that into invasive and non-invasive, I think the invasive kind would, unless it shows a significantly huge bonus, would still remain in the realm of the medical domain, except for those who want to adopt it, the early adopters who are sort of exploring technologies. One has to definitely keep in mind that invasive technologies, despite being invasive, have much higher resolution, much higher spatial and temporal resolution than non-invasive devices. So there is definitely already an edge that invasive technologies have over non-invasive technologies. But you can imagine that non-invasive technologies might be useful in, as you say, one of them could be recreating a realistic experience in VR, where you're able to have sight, sound, smell, touch, and taste. So far you can actually, there are a lot of shops that have VR experience, which includes haptic suits, and that can actually make you feel and sense the touch or the push of any object. But imagine you go to the next level, that you can actually also smell and taste the object without the object actually being there. As sort of scary as it sounds, I think it's really exciting to see that you can recreate something of that sort, because I think the ways that technology can help our lives sort of in a way which is making us mentally at a sort of better situation, if you will, whether it be through entertainment, whether it be through recreating memories, is something that brain-machine interfaces could find a huge application space in. There are already a number of companies that are selling devices that are purportedly helping improve performance, improve athletic performance, memory, muscle memory, and so on and so forth. I think that's sort of just the beginning, but without going into sort of too many details of really distinguishing the valid scientific output with non-scientific output, I think that domain would definitely find a lot of use in the non-invasive space.
Right, right. Yeah, yeah. I mean, I'm going to jump a little bit. Linger on to the virtual reality and augmented reality space, because you yourself are vested in the building an AR interface. The movie Spider-Man. The last movie of Spider-Man. The Edith glasses which Tony Stark gives Spider-Man. How long do you think? How far are we something from something like that?
That's a good question. I think if you were to imagine there being a device in the future which can extremely realistically in real time recover all the textures, the colors, the smells, and everything, that would be a tough ask. I'm not saying it's impossible, but it would be a tough ask to do, simply because of the computational power that you need to recreate things. But then, having said that, I think there are always these leaps by which technology moves forward when people suddenly find that there is something that they've been overlooking, and that suddenly gives them a much more realistic technology or much more realistic experience as compared to the previous generation ones. And I can see such leaps happening definitely over the next decade or more, where you would have much more relatable technology that's being developed. Having said that, I think, as we started in the beginning, the brain itself is still being understood, and so it's not that evident where you can read out a person's brain signals when he or she is undergoing an experience and say that, okay, this part is being excited because he's smelling, the roses. This part is being excited because he sees a cup of coffee there. So breaking down reality into a component of signals and then using that to recreate the reality is going to be a tough mapping, if you will. But I can see approaching some semblance of what might be sort of living an experience in a parallel life as a means of entertainment. And I think where it's interesting is that one would have to consider the implications, as we talked about earlier, also about, okay, what if someone goes into this reality with an extremely realistic brain stimulation system where he or she feels that is more real than the real world, or he or she feels more comfortable there than being in the real world. So those sort of questions will definitely start popping up in the near future, because you can already see technology approaching limits of recreating things or addressing things in the brain that we never thought we could a decade ago.
Right. Yeah. So yes, I think we're living in the most awesome time in human history. Just close to 40 or 50 years back, computers were as big as my room, and the technology is growing on an exponential space. And at this point in time, I think what these disruptive technology is doing is that I think in another few decades, it's going to shatter everything that we thought was impossible. And that's the reason for my show. That's the reason my show is called Change, I Am Possible. Because I believe that we're living in a fantastic world where the only thing that you're restricted by is the limitations you put on yourself. And I think impossible is nothing. Like I was having this conversation with this doctor who's figured out a way to reverse aging through young blood transfusion. Then I was having a conversation with somebody in quantum computing, and I'm saying, whoever I talk to, there is so much I get to know, and every single day and every single conversation, my belief gets stronger that we are living in a world where everything is possible. And in due course of time, whatever we term impossible right now will be shattered. Because I think a human belief, I think, is the most important thing. And that's the reason, if you see, these novelists, these authors, these creative movie makers, they always show you what is in the realm of possibility by writing about it or showing it in the movies. And then there are these scientists or researchers, and they say, oh wow, he said that's possible. Now let me just go and look back at the physics of the science of it, and oh wow, it actually doesn't seem that impossible. And so I personally believe that impossible is nothing. So can you talk about Parc's legacy work on user interface and how you're building on that to define future brain machine interfaces?
Sure. So just I'd like to quote Arthur C. Clarke, who's a very well-known science writer, who said that if a distinguished scientist tells you that something is possible, then he is very certainly true. But if they tell you something is impossible, then he is very likely wrong. And that's sort of the spirit with which I think a lot of science and technology development takes place, in the sense not of a sort of a healthy skepticism where you believe that what is so far has not been possible might be possible in the future. And so Parc has been sort of consistently aiming at making technologies that have not been thought of before, but which in due course become so commonplace that you cannot think of living without them. Even take, for example, laser printers, the mouse, the Ethernet, graphical user interface. A lot of these technologies are what are the foundations that have allowed the building of more advanced stuff that allow me to have this conversation with you right now. So I think Parc's legacy of making user interfaces that are genuinely sort of amicable to a regular usage is something that is manifesting in this idea of user interfaces with brain computer interfaces. And it could be, for example, that in the future office, you think of a tool that allows you to be much more productive and simultaneously be in touch with a lot of your other colleagues, for example, at the same time, in a form where it allows you to be in the network rather than on the network. So it's sort of you literally immerse yourself inside it by the use of such technologies. And I think the importance of having such technologies is highlighted right now in the current situation of the COVID-19, where everyone is sort of working from home. What used to be earlier considered a luxury, that, okay, I don't have to go to the office building, I work from home. Now everyone is being sort of forced to do it. But at the same time, that there is this realization that I'm missing that realistic office interaction. I am missing that sort of 3D feel of things, of moving around and being in some place and knocking on someone's door and having an interesting conversation. And I think if you can enable a technology that allows you to be remotely sitting anywhere you want, but feel as realistic as being literally in your own office and opening the door, moving to someplace, knocking on someone's door, having a meeting, pulling a chair, sitting down, that would be a significant achievement, and something which can find a long-term ubiquitous usage as sort of as commonplace as saying, let's Xerox this document, for example.
Right. Yeah. So yes, I think we're living in exciting times, and somehow most of the technologies, when it gets so common, we don't even give it importance, and that's when it gets ubiquitous. It's there everywhere, and we don't really, right now we keep on harping about artificial intelligence, virtual reality, and stuff like that. But I think in the near future, it'll be just part of who we are, what we do, how we live, work, and play. So Krishnan, it was a pleasure talking to you. I personally am super excited about brain-computer interface, mainly because I think it'll play a major part in enabling virtual reality into being what it intends to be. Right now we just kind of understanding the technology, and there are these, obviously, these drawbacks, these hardware software drawbacks. I believe brain computer interface will play a huge role in enabling what virtual reality can and should be. So I'm excited because of that. What are you excited about the future of brain computer interface, and what's your moonshot?
Okay, so there are a number of things that excite me as far as science and technology are concerned, but in particular, what has interested me in brain computer interfaces is the use of it as a tool to really probe ourselves. Because at the end of the day, I think subconsciously, a lot of people, the sort of the understanding or the intent is to bring peace and happiness on ourselves. But then if you go to the next level of asking, okay, but who are we? Like, who is the person who is feeling happy? Those sort of questions which start to hit upon more philosophical topics. I think 2-3 decades ago, one would have thought, okay, they would be in the realm of philosophy. But now with the advent of such brain-computer interfaces and technology, you can actually probe things like states of awareness of a person. You can probe things like emotions. You can probe things like the difference in the facial expression versus what they're actually feeling inside. And if you think of the extreme extrapolation of this, which is the concept of qualia, which is the fact that what I am experiencing right now, I cannot fully transfer to you, because you cannot have the experience of everything that I've experienced so far to build on that and feel what I'm feeling. But imagine a situation where you can literally take a person's personality, mental state of mind, and at the click of a button be like, okay, you know what, this is what I'm feeling like. Can you feel what I'm feeling right now? That concept of being able to transfer the complete experience that I am feeling to someone else is something which is very interesting technology wise, but also sort of philosophy wise. It gives an insight into who we are, what makes us happy, and what sort of at the end of the day brings us peace. So I think for me, it's sort of an understanding of philosophy as well as of practical physics applications of such devices.
Lovely. Krishnan, thank you. Really appreciate you giving time and sharing your insight. I personally am super excited about BCI. Even right now, it's enabling the physically disabled or physically challenged. And you said, I mean, what it can do, like transfer experiences, transfer thoughts, maybe like a hive mind where we are all connected. We're living in exciting time when we're just probing the possibilities of what can a brain-computer interface can really do. And let me end with this note where Elon Musk keeps on stressing. Artificial intelligence is growing at an extremely rapid pace. And there is a need for us to, if we need to stay relevant, I think we need to converge with machines. It might sound a little harsh to the people who are not very technologically inclined, but I guess that's the truth and that's the fact. And we need to listen to leaders like that, and we need to build these brain-computer interface if we have to stay relevant. Krishnan, really appreciate you being part of Change I Am Possible podcast. And to my listeners, if you like what you see in here, please press the subscribe button. Thank you, Krishnan. Really appreciate you being part of Change I Am Possible podcast.
Thank you. Really appreciate it. Thank you for having me over.